Okay, let me go over the calendar real quick here. Yesterday, during the help session, I went over triangulator rates and inverse trig. I went over some of the homework problems for 5.6. Then I also pulled from triangulator rates from the test review packet, just to get some practice in. So today we're going to start our test review packet. Everyone should have the test review packet. Is anyone missing the test review packet? Okay, so we'll spend today going over test review worksheet 1, Thursday worksheet 2, Wednesday, Friday worksheet 3, and then we'll do some miscellaneous practice on Monday, and then your test is on Tuesday. I will have help sessions starting tomorrow morning. I'll send out a reminder this afternoon. It'll be over Teams as well as in the classroom. So I'll just pick out problems. Either I'll redo problems or I'll just continue to hit the topics that we're going to be seeing on the test. If you have any test recoveries that you want to make up, you can do it on that makeup days next week. And I will be looking to see if I can identify students who may want to do recovery for the trig unit test. So I'll try to grade those, give a quick turnaround to the students who may need it, and then I'll let you know. So if you hear from me Tuesday evening, or if you see it graded in the grade book, that means there's an opportunity for you to do recovery. Okay, so if you don't hear anything from me Tuesday night, then that means there's no recovery for you because you made 75 or above. Okay. But also, if you're not here on Tuesday, then you'll have to pick one of the days to come in and make that trig unit test up. Okay. So, okay. Any questions about our calendar here? If there's anyone who wants to take the test early, you'll have to come talk to me and just let me know when you want to take it. But I think for most of us, I think only a few students have approached me about taking it earlier. But if you want, yeah, so I think most of us are going to take it on that Tuesday. Okay. So let's go to our test review packet. And if you can go to the very last page here, page 30. These are the topics. You're looking at about 6 or 7 problems because some problems are split up into 2 parts, or some problems are split up into A, B, and C. Okay, so page 30 in your packet. These are the topics that we're going to focus on. Inverse trig derivatives. So being able to find the derivative of inverse trig. Sometimes they may involve products, chain, quotient, rule. So, but the important thing is what we did on Monday with practicing those derivative, finding derivatives involving inverse trig. Second is implicit differentiation involving trig. So finding tangent equation. You know that you have implicit differentiation whenever you have variable y inserted into the equation, right? If it's not y equals, then there's going to be implicit going on. Particle motion problem involving trig. We will brush up on that either today or tomorrow. Related rates trig. We'll do one of those today. Or actually, we may not get to it today. We may get to it tomorrow. Mean value theorem, trig derivatives, average rate of change. This is one of the extended problems that we'll work on today. Trig curve sketching problem. We focused on that for 2 days, so we'll revisit another problem like that tomorrow. So it'll be either a sine or cosine, okay, function, and how the graphs will move. Okay, so we'll do a practice with that over the next few days. Okay, so these are the things you want to make sure you memorize. Okay, unit circle values. So I will give you a blank unit circle if that will help you with those values on the day of the test. Make sure you know your derivative rules for natural log of u and e to the u, right? This is u prime over u, this is e to the u times u prime. Those will show up on the test. Make sure that we know that. So obviously power rule. And then trig derivatives, the original six trig derivatives that you demonstrated on the quiz. Those rules need to be memorized. And then inverse trig derivatives, right? We talked about how there are 6 of them, but it's really only 3 that is unique. And then the other 3 are just negative versions of the ones that we see there. Hey, no calculators. Okay. Okay, so you can turn to page 1 in your packet. So what that means is there's no limits. Okay, so I put limits here for I put it on previous test, but it's not going to be on this test. So no limits. Okay, so let's look at number 2. Number 2 is Rolle's theorem. Rolle's theorem falls under the category of mean value theorem. So let's walk through this step by step here. Okay, so Rolle's theorem, the whole point of Rolle's theorem is to see, can we guarantee a place on the graph where there's a slope 0? Right? So Rolle's theorem is trying to figure out, is there a slope 0 somewhere along the curve? Mean value theorem is related, but mean value theorem doesn't have to be a slope 0. It can be slope 1, slope 2, slope -5. It depends on whatever slope is found between the endpoints. Okay, but Rolle's theorem is specifically looking for slope 0. So it doesn't matter if it's a relative max or relative min, it just needs to be a slope 0. Okay, so let me copy this again. Okay, so it says determine whether Rolle's theorem can be applied. If so, find all the values such that f prime of c is equal to 0. So that's exactly what we're trying to do. Try to find out c value where the slope is 0. We have to first confirm a couple of things, right? There's 3 conditions for Rolle's theorem: continuity, differentiability, and then the endpoints have to be the same y value so that we can guarantee that slope 0. Now, we never have to worry about differentiability with trig functions, okay? Every part of a trig function is going to be a smooth curve. We're never going to have a sharp turn, but there's a possibility that we have to worry about continuity. So with anything that's not sine or cosine, we're going to experience potential vertical asymptotes. So in order to know where the asymptote is for secant, we can rewrite secant as what? 1 over cosine. It feels more familiar, right? So as soon as you see a variable in the denominator, you know that there is a potential for a break in the graph. So whatever makes the denominator 0 is where your vertical asymptote is going to be. So let's list out some places where cosine is 0 and see if those asymptotes interfere with the interval that we have in this problem. So where is cosine equal to 0? Pi over 2, 3 pi over 2. Oh, thanks so much. So not only that, notice that my domain is in the negative region. So I'm going to just call out some negative values as well. I'll subtract 2 pi from both of these. And so I'll get negative 3 pi over 2, and I'll get negative pi over 2. All right. So let's think in terms of a number line, right? And see if any of these asymptotes interfere with my interval. So here's what my sound line could look like, right? So here's 0, here's negative pi over 4, and here's pi over 4. Okay, so now pi over 2 is further to the right of pi over 4, and then 3 pi over 2 is to the right, and then if I do negative pi over 2, that's going to be over here, and then negative 3 pi over 2 is over here. So are any of the asymptotes going to interfere with my interval? No, right? So we're safe, right? So we have all these asymptotes, but those asymptotes are all falling outside of the interval for our problem. So our continuity statement is safe. Okay, so we can say our function is continuous on the closed interval. And if it's continuous, then we know it's differentiable as well. Okay, so just have to make sure we, oops. Okay, what's next? Into the original function, right? So no derivative yet. The next step is going to be the same, whether it's Rolle's theorem or mean value theorem. We have to find out what's happening at the endpoints. Okay. So we want to find the order pair at negative power 4, and also the order pair at power 4. I'm going to put into that 1 over cosine. It just feels more familiar, but okay. So if negative power 4 doesn't feel familiar, you know that a coterminal version of that measure is 7 power 4. I can add 2 pi, and we know it's in the fourth quadrant. So cosine in the fourth quadrant is positive. We know it's root 2 over 2. But then if I were to flip that into the numerator here, I get 2 over root 2. So that's fine. You can leave it like that, or you can write it as root 2. They mean the same thing. Okay. But we just want to find out what the y value is. Okay. Let's find the y value at the other endpoint. So cosine of power 4, that's in the first quadrant, 1 over or root 2 over 2 in the denominator. If I flip that, I get 2 over root 2. So same thing. Okay. So does it pass Rolle's theorem? Yes. Okay. Because these are the same y value. What can I say about the slope? 0. Yep. Change in y over change in x. Right. Root 2 minus root 2 is 0. 0 over anything is going to be 0. So there's our slope target. Now we can do what? Derivative. Yeah. So we're always setting the derivative equal to whatever the slope is. Now, the difference with mean value theorem is that these two numbers may be different. If it is, we still find the slope. We just are not going to always guarantee a slope 0. It can be slope 1, it could be slope 2, it could be slope 5. But Rolle's theorem has to be slope 0. Okay, let's find f prime. What's secant's derivative? Yep, secant times tangent. So we're going to set secant tangent equal to 0. Things feel more familiar if I can get this in terms of sine and cosine. I think we just prefer to think in terms of sine and cosine. We can recall values faster, right? So if I multiply that out, it's really just sine of x over cosine squared x. That's my derivative. Okay, so I want to know when my derivative is equal to 0. Now, if I'm doing Rolle's theorem and I'm dealing with a fraction, where do I look for slope 0? Just the numerator. Good. Rolle's theorem is just the numerator. Now, if it was a critical point problem, if I asked you for critical points, first derivative test, slope sine line, then we're going to set the denominator equal to 0 because we want those places where slope is undefined or to be on the sine line as well. But Rolle's theorem is just slope 0. We don't want slope undefined. We only want slope 0, so just the numerator. Okay. So where is sine equal to 0? 0, pi, 2 pi. Now let's go into negative as well, just so that we can cover our bases. So negative pi, negative 2 pi. Now with Rolle's theorem, we're guaranteed at least one solution. So is there a solution here that lands between negative power 4 and power 4 that we can use? 0. Yep, that's the only solution. All right. Once you get to this point, you're guaranteed at least one solution. So if you go through your work and you see that nothing falls inside the interval, something went wrong. Okay. So if you got this far, guaranteed at least one solution. Okay. Any question here? Rolle's theorem? Yeah.
Why did you do that?
Oh, why not do negative pi and negative 2 pi or?
Above. when you First started, when you go to.
Oh, right. So I found because my intervals from negative power 4 to power 4, so I just want to make sure that these asymptotes, the different locations of these asymptotes are not going to interfere. So I just subtracted 2 pi from pi over 2 and 3 pi over 2 just to find my other asymptotes and make sure that these negative asymptotes don't interfere with my negative interval. So I just included that just so I can cover my bases and just have that peace of mind that I'm not overlooking something. Okay, let's look at number 3. Number 3 says apply mean value theorem to our function on the interval from 0 to pi. We're still going to make sure that we have our conditions set. What's nice about our conditions for this function? Yeah, they're both true because sine function has no asymptotes, right? Sine and cosine are safe. We can just go ahead and state our conditions without having to worry about any breaks or any sharp turns. Okay, so after we make our statement about continuity and differentiability, what's next? Plug into the original. Good. So no derivative, right? So mean value theorem, Rolle's theorem, you gotta handle all of your algebra steps before you jump into the derivative. So don't do derivative too soon with Rolle's and mean value, because otherwise you may skip a step. Okay, so our function is continuous without having to worry about anything differentiable on the open interval. And then we're just going to work towards getting to our endpoints. So plug 0 in for x, and also plug pi in for x separately. So 2 sine of 0, what's sine of 0? 0. And then 2 times 0 is also 0. So sine of 0 is also 0. Okay. And what about sine of pi and sine of 2 pi? Also 0, right? So what's the slope going to be? 0. So this could have been a what? Right, this could have been a Rolle's theorem, but mean value theorem also encompasses Rolle's theorem. So it just so happens that this ends up being slope 0, which could be a possibility, but it's just not guaranteed with mean value theorem. So mean value theorem can be slope 0, but Rolle's theorem has to be slope 0. Okay. So my slope is 0. Okay, good. That's my target slope. I'm going to be setting my derivative equal to my slope. So let's go ahead and find our derivative. 2 sine x becomes 2 cosine x. And the sine of 2x becomes what? 2x times 2. Yep. Sine of u becomes cosine of u times u prime. So we're going to set our derivative equal to the slope between the endpoints. Do some cleanup here. So I get 2 cosine x plus 2 cosine 2x equals 0. I have that double angle identity that I have to resolve. So I'm going to pick the one that has only cosine in it, since everything else is cosine. Now, if you see a double angle on your test, I'll give you the formulas for them so you can apply it. So I'm not going to ask you to memorize those double angle formulas. Okay, so we choose the one that has cosine in it to make it quicker to our solution so that we can just get it all down to one trig function. So cosine 2x can be expanded into 2 cosine squared minus 1. Okay, distribute that through. And we get something that we can factor. So I'm going to rearrange it. Cosine squared followed by cosine followed by the constant. PCF then it becomes a trinomial factoring, right? Divide by 2, the 2 goes away. So if it's easier, we can try to factor in terms of just x. So why don't we just do an easier problem here? 2x squared plus x minus 1. You want to go through star method, it's multiplies to be -2, adds up to be 1. So what two numbers adds up to be -2, multiplies to be -2, adds up to be 1?
Positive 2 negative 1.
2 and -1. Okay. So that's my star method there. 2 is in the denominator, 2 and -1. Fraction ends up being 1 and -1/2. Bring the denominator 2 to the front. But now I can bring cosine back in because I'm not really factoring in terms of x, I'm factoring in terms of cosine here. So now just solving for cosine and looking for unit circle values. Okay, so where is cosine going to be -1? Yep. Just pi, right? Okay, and where's cosine going to be 1/2? Yeah, first and fourth, right? So in that pi over 3 family, pi over 3 and 5 pi over 3. But our interval is just between 0 and pi, so it's pi over 3, right? Even pi is outside the interval. Why is pi outside the interval? It's an endpoint. Okay, so mean value theorem and Rolle's theorem, my solution x value has to be inside the interval. Endpoint is not good enough. It's got to be between. Okay, let's do a full trig problem. Particle motion on the back. Or particle motion and mean value theorem, it kind of merges together here. More mean value theorem though. So number 4. Okay, an object's position is given by f of t. It's continuously differentiable, so they're already stating that for us in our domain from 0 to 3 pi. F of t is given in meters. Find the average velocity. Okay, so we're going to be working with this function, plugging in and also find the derivative down the line. What can we do to make this easier to read? We could. I was talking about that cube. Now, cosine, maybe we can deal with that later if we want to flip it. But what I want to make sure is we understand that exponent is not in a location that is beneficial for us interpreting. It's harder to, even though it's easier to write, it's harder to interpret. So I really encourage you, whenever you're working on the problem, rewrite it, get that exponent to show outside a set of brackets so you know which order you're working things on. Okay, so now part A is asking for average velocity. Does anyone know what the definition for average velocity is? Change in what? Position, yeah. So the thing that's tricky about this is that average velocity, we're not going to touch the velocity function. Okay, it's because of the word, this word average. So average is telling us that this is really a slope of position between the endpoints. So this is going to be the change in position divided by the change in time. So we have our endpoints 0 and 2 pi. So we just have to find the slope between the endpoints. So change in position over change in time. So f of 2 pi minus f of 0 over 2 pi minus 0. So that's what we're looking for. Change in position over change in time. So that means I have to plug 0 and 2 pi into the original function, right? We're not going to find the derivative. We're just going to stick with position here. So I'll put 0 in for p. Now, secant of 0, maybe secant of 0 doesn't ring a bell, but let's think in terms of cosine, and then we can flip a result, right? So what's cosine of 0? 1. 1, right? Cosine of 0 is 1. So if I flip 1, I still get what? Still get 1. Well, the original domain is 3 pi, but for part A, it says find the average velocity from 0 to 2 pi. Yeah, so basically they changed it for part A. Okay, what's 2 pi over 6 reduced to be? Pi over 3. Let's think in terms of something that's more familiar. Instead of secant of pi over 3, let's do cosine of pi over 3. What's cosine of pi over 3? 1/2. So if I flip it, it becomes secant, right? So 1/2 flip becomes 2. Make sure that you take care of your exponent before you do multiplication. So do the 2 cubed first. 8 times 2 is 16. So now the slope between these endpoints is the average velocity. Okay, this reduces to be 14 over 2 pi. What does that reduce to further? 7 over pi, right? So that pi doesn't float up to the top. It needs to stay in the denominator. So 7 over pi. So my average velocity. Okay, what's my unit of measure here? Meters per second. Okay.
Did you get a 2 per secant, 2 pi over 6?
Right. So I broke this down here. Because 2 pi over 6 is the same thing as pi over 3, right? Secant of pi over 3 doesn't feel as familiar to me. So I found cosine of pi over 3 instead. Right, what's cosine of pi over 3? 1/2.
Oh, yeah.
So then if I flip 1/2 around, I can get to secant. So 2 over 1, which is 2. Okay. All right, so that's part A. Any questions so far? All right, look at part B. Okay, at what point in time does the instantaneous velocity equal the average velocity? So we need to recognize this as basically rewording the definition of mean value theorem. Okay, because this is what mean value theorem looks like. Right, mean value theorem is f prime of x equals f of b minus f of a over b minus a. But if we want to reword it in terms of particle motion, f prime is the same thing as what? Velocity, right? And that's the same as velocity. And then f of b minus f of a, change in position over change in time, is the same thing as average velocity. So really, going through this process of setting the velocity equal to the average velocity is mean value theorem. Right? So we basically are asking, okay, I know I have my average velocity of 7 over pi. I know there's some point along this journey where this particle is going to hit exactly this velocity, and we want to find that point. So we want to set the velocity equal to 7 over pi, but it's only asking us to set it up. We're not asked to solve it. We just have to set the equation up. Okay, so if we want to find the derivative to get to velocity, okay, so I have that bracket sitting outside, that exponent sitting outside my bracket. What do we have to involve here if I want to find the derivative? Chain rule, right? I got that outside inside portion. Without that bracket in the cube, it's harder to see. So my outside portion is 2 bracket cube. And my inside portion is that secant of t over 6, which is, you can think of t over 6 as 1/6 t if you like. Okay, so let's break this down step by step. What's outside's derivative? 6 brackets, get 6 brackets squared. So we do that first. There it is. And then we got to do inside's derivative. So secant of t over 6 becomes what? Secant. Tangent t over 6 times u prime. So 1/6 t becomes what? What's the derivative of 1/6 t? Just 1/6, yeah. Okay. Outside's derivative, inside's derivative. So we basically have our velocity. We have our average velocity. We can just put them together, set them equal to each other. Oh, I'm doing some cleanup here. The 6 and 1/6 can cancel out. I can merge the secants to become secant cubed, but I don't have to do any work beyond that. I can just set my instantaneous velocity equal to my average velocity. If I were to solve for t, I'll be able to find what that t value is, but this is more complicated than what we intend to do, so just have to set it up. Part C. Part C says, what is the instantaneous velocity of the object when t equals pi seconds? So what's the strategy here? Plug pi into the velocity. Yep, we just find v of pi. So here's my velocity function. I just have to insert pi into my velocity function. So there's my cleaned up velocity function. Right, the 1/6 and 6 cancels out. The secant merges. I'm going to bring that 3 back out again just so that it's easier for me to plug in. So I'm going to bring that 3 outside my set of brackets. I'm going to replace t with pi and see if I can evaluate each of these. So secant of pi over 6 feels less familiar. So what's related is cosine of pi over 6, right? What's cosine of pi over 6? Or 3 over 2. So secant of pi over 6 will just be what? 2 over root 3, right? Okay. And then tangent of pi over 6, that's my order pair at pi over 6. What's the tangent of pi over 6? Yeah, so y over x, right? So 1 over root 3 or root 3 over 3, either way. So there's my cosine flipped. And there's my tangent. You can do root 3 over 3 or just 1 over root 3, either is fine. Okay, I'm going to cube my first term there, 2 cubed root 3 cubed, the same thing as root 3 times root 3 times root 3. 2 of the root 3 becomes 3, and then the root 3 is going to hang out, so it's 3 root 3. Continue multiplying. So root 3 times root 3 is 3, 3 times 3 is 9, so 8 over 9. That's my velocity. My velocity is 8/9 meters per second. Okay, part D should feel pretty much the same as C. What is instantaneous velocity when t equals 2 pi? So what do we do here? Yeah, 2 pi into the velocity function. So same steps as C, it's just a different t value to plug in, right? Two pi over 6, the same thing as pi over 3. Secant of pi over 3 is the reciprocal of cosine of pi over 3. We know cosine is 1/2, so secant must be 2 over 1. And tangent of pi over 3 is just root 3 over 1 or root 3. Okay, last one here, part E. Find the equation of the tangent to the graph of t equals pi, 2 pi. So what information do we need? Find the slope and find the y value. So y value is just plugging 2 pi into the original function. Do we already have something that we can use for part E? Yeah, part D, we found the velocity at 2 pi, which is same thing as the slope at 2 pi, right? So we can carry that 8 root 3 down. That's same thing as f prime of 2 pi, right? So the only thing left is to find the y value at 2 pi. So put 2 pi back into your original equation. So my original equation is 2 brackets secant t over 6 cubed. Replace t with 2 pi. And then just evaluate slowly. So secant of pi over 6, secant of 2 pi over 6, same thing as secant of pi over 3. We know secant is related to cosine. Cosine of pi over 3 is 1/2. Flip that around, I get 2. 2 cubed is 8. 8 times 2 is 16. Okay, so everything we need is in front of us. We have our ordered pair. We have our slope. Now we can do point slope form. Okay, so y minus y sub 1 equals to m times x minus x sub 1. Yeah, I brought t back in because our original independent variable is t. Yeah, you could use x, that's fine. Okay, any questions? Okay, tomorrow we will do worksheet 2. We will work with implicit equation, implicit differentiation. We'll do a related rate, and we'll do a curve sketch. Okay. All right, go and get your phones.
Then